In this lesson, we're going to explore the third type of transformation that functions can undergo. So far, we've talked about translations and reflections. Today, we're going to talk about dilations. So just as a refresher about what we've been talking about, we want to take a look at this first function where it says graph the equation y equals negative, or f of x equals negative x plus 3 squared plus 1. So when we are going to graph these equations, the first thing that we want to do is identify what transformations are happening and then come up with our mapping notation, which will help us get 5 points for our new function, our child function. So if we look at this, we see that this minus sign is going to be, that represents a reflection over the x-axis because it is affecting our y values. This plus 1 is going to be a translation up 1 unit. And then in here, the x plus 3, because the x always lies, this is going to be a translation left 3 units. So if we were going to come up with a mapping notation, our mapping notation that would take our parent function's points to our child function's points would be equal to, we would have to move left 3, so x minus 3. And then we would have to take our y values and make them the opposite value and then add 1. And so to get our new points for our child function, we would take our parent function points, which are over here, and we would subtract 3 from each x value. So that would give us negative 5, negative 4, negative 3, negative 2, and negative 1. And then we would make our y values the opposite sign and then add 1. So 4 would become negative 4 plus 1, that would be negative 3. Negative 1 plus 1 would be 0. 0 plus 1 would be 1. And then we'd have negative 1 plus 1 would be 0. And then negative 4 plus 1 would be negative 3. And so that would give us our child graph. And then we would plot these points and have our new function. So we'd have negative 5, negative 3. We'd have negative 4, 0. Negative 3, 1. Negative 2, 0. And negative 1, 3. And so we have our parabola that is opening down now, looking like that. So that is just a refresher of what we have been talking about up to this point between translations and reflections. We are going to skip example A for this set of notes, and then jump down here and take a quick look at dilations. So we're jumping straight into the final transformation. First of all, you should know that a dilation is something that is going to stretch or shrink a graph. It's going to change the size. So this dilation that occurs is going to happen by the same scale factor for both vertical and horizontal dilations. So whatever the vertical dilation is, every point will change by that scale factor. Whatever the horizontal dilation is, every point will change by that factor. It's not going to happen to individual points, it will happen to all the points. So when we look at a dilation, today we're going to start by looking at the parent graph y equals the absolute value of x. The typical form, when it is written as a double lie, is going to be y minus k divided by b equals the absolute value of x minus h divided by a. And what we're going to have is the b and the a are going to represent the vertical. So b is going to be the vertical dilation. And then a is going to be the horizontal dilation. And so whatever number that you have there, that's going to tell you how your x values and y values are shrinking or stretching. So you could also write this right here is written as a double lie. You could also write this as a single lie, which would look like this: y equals b times the absolute value of x minus h divided by a plus k. And the general form, because we can apply this to any of the parent functions that we've looked at, would be y minus k divided by b equals f of x minus h divided by a, where f can be any of the functions. I put a few examples here of each of the parent functions. You have your quadratic parent function written with the dilations. So on the top, you have the double I. On the bottom, you have the single I. And then here's the square root function written with the dilations. Again, the top is the single I, and the bottom is the double I. So let's take a look at the absolute value family. So if we look at this, what we see is this equation, y divided by 2 equals the absolute value of x. Again, you want to take a look at this and see what transformations are happening. So this is written as a double I, and this 2 represents a scale factor. So this is a vertical dilation because it's underneath the y. Our y values are going up and down, so vertical. This is a vertical dilation, and it's going to be by a scale factor. So SF represents scale factor of 2. And because this is a vertical dilation, and because this is a double I, what this is saying is we're going to take our y values and multiply them all by 2. So our transformation would look like this. X's stay the same, but then our y values are being multiplied by 2. Again, because this is written as a double I. As a single I, it would look like this. And again, since there's nothing in this grouping with the x, that means there's nothing happening to the x values, they're staying the same. And then this 2 is representing the vertical dilation because it is affecting the y values, and it is that is written as a single I. We know that we'd be multiplying our y by 2. So again, if we were going to graph this, our x values would stay the same. So we'd have -2, -1, 0, 1, 2. But then our y values would then be multiplied by 2. So you'd have 4, 2, 0, 2, and 4. And so that would produce this blue graph right here. This blue graph is y divided by 2 equals the absolute value of x. The blue graph, or letter B, you have y equals x divided by the absolute value of x divided by 3. And so this is going to be a horizontal dilation by a scale factor of 3. And so again, this being this is written as a single lie, x always lies here. We know that our transformation is going to take our xy points and it's going to multiply x by 3, but the y stays the same. And again, you're going to take your parent function graph, the 5 points that we have, which are right there, and that would change to all your x values being multiplied by 3 and all your y values staying the same. So 2, 1, 0, 1, 2, but then -6, -3, 0, 3, and 6. So all the x values get multiplied by 3. And so that would be your purple graph right here. So the purple graph is going to represent y equals the absolute value of x divided by 3. Next, if you look at graph C here, or equation C, you'll see that it has both A and B in it. So you have your scale factor of, you have a vertical dilation of scale factor 2, and you have a horizontal dilation of scale factor 3. And so if you take this, written as a double lie, your transformation here would take xy, and it would multiply the x values by 3 and your y values by 2. You could also see this written as a single lie, where it'd be y equals 2 times the absolute value of x divided by 3. So again, you take these, you take your parent function, and you take the 5 points in there, and you multiply your x values by 3 and your y values by 2. So that would give you -6, -3, 0, 3, and 6. And then your y values would be 4, 2, 0, 2, and 4. And so that's going to give you our red graph here. So this red graph would be y divided by 2 equals the absolute value of x divided by 3. And finally, in part D, we're going to put all of this together. We're going to have our dilations, and we're going to have our reflections and translations. So when you're looking at this, the first thing when you're trying to go from your mapping notation or from your equation to your mapping notation, the first thing that you should do is see, do you have any dilations? Do you have any reflections? So again, we have a reflection over x axis. We're going to have a horizontal dilation by a scale factor of 2. We're going to move left 1, and then we're going to move up 3. And so if we're going to write this mapping notation, we have to figure out what's affecting our x values. So the first thing that we see is this is written as a single lie. So our x values are still lying. It says you're dividing your x by 2, so that means you're going to multiply by 2. So you have 2x, and then you're moving left 1, so it's going to be 2x minus 1. Our y values are reflecting over the x-axis, so it's going to be opposite y plus 3. And then you take your parent function to create your graph. You have x, y, and you take your x values, and you're going to multiply them by 2, and then subtract 1. So you're going to have -4 minus 1 is -5. You're going to have -2 minus 1 is -3. 0 minus 1 is going to be -1. Then you're going to have 2 minus 1, that's going to be 1, and then 3. And then for your y values, you're taking the opposite y and adding 3. So -2 plus 3 is going to be 1. You have -1 plus 3 is going to be 2. 0 plus 3 is going to be 3. And then you're going to have 2 and then 1. And so that graph is going to be this blue function right here. That is going to be y equals negative absolute value of x plus 1 over 2 plus 3. Again, that final example combined all the stuff we've talked about into one problem. Now, again, it is my advice that when you are graphing a function, the first thing that you should do is look at the dilations. You want to figure out what the dilations are and then figure out what the translations are. That's going to help you avoid moving the vertex. But when you're finding the equation for a graph, so if I give you the graph and you are trying to find the equation, you want to figure out the translations first and then the dilations and reflections second. Again, us talking about these different transformations, translations and reflections are rigid motions. They are going to produce an image that is congruent to the original image. It does not change the shape of the graph. But vertical and horizontal dilations, they're going to change the shape. And when something changes the shape, it is considered a non-rigid transformation. So what we're going to do is we're going to take a look at examples C and D. Example C, we're going to take the equation and go write it as a mapping notation. And then for example D, we're going to take the mapping notation and rewrite it as the equation. So we will do A and C together, and then you will try B and D, and you can check your answer on the completed notes. So first off, again, when you're writing the equation and when you have the equation going to the mapping notation, you want to take a look at what are the dilations first. So if I look at this, I see that I have a vertical dilation of a scale factor of 3. And then I have this, which technically can be rewritten as 3 times the square root of x over 2. And so what that allows me to do is see that I have a horizontal dilation of a scale factor of 2. And because this is written as a single lie, that tells me that my mapping notation is going to take my xy values to, the x always lies, so it says x divided by 2, so I'm going to have 2 times x. But then the vertical dilation is written as a single lie, so that's going to be 3 times y since we're multiplying by 3. In letter C, you take a look at this, and there's going to be a little bit of extra work that you have to do. You want to see it, you look at this and you say, okay, I have a vertical dilation of scale factor 1/4. So I'm multiplying by 1/4. I have a vertical shift, So I'm going up 2. And then inside of here, we have a dilation and we have a translation. So what we want to do is first figure out what the dilation is. And when you have something written like this, where you have 3x minus 9, what you want to first do is factor out any kind of common factor. So in this case, you have 3 times x minus 3. And so what this shows you is that you're not really moving 9 units to the right, you're really moving 3 units to the right. So we have a horizontal dilation of a scale factor of 3, or a scale factor of 1/3, because that says 3 times. So again, really, when you're right there, you're really dividing by 1/3, and then you're moving left or right 3 units. And again, what we see here is this x minus 3 times 3 could be rewritten as x minus 3 divided by 1/3. And when you divide by a fraction, you're actually multiplying by the reciprocal. So our transformation here would be equal to, again, we have a horizontal dilation of 1/3, so it's going to be 1/3 x. We're moving right 3, so plus 3. And then our vertical dilation is 1/4, so 1/4 y plus 2. And again, you're going to do C, B, and D and check your answers on the completed notes. Now we're going to take a look at example D, where we're going to take the mapping notation and rewrite the equation based off of that. So in this mapping notation, what we see is that there is a vertical or a horizontal dilation by a scale factor of -2. So there's a horizontal dilation, and then we have a vertical dilation. And so if we want to write this, again, we're using the absolute value equation. We would have y equals our vertical dilation, which is 3, times, we have x, we're multiplying by -2, so now we're going to divide by -2. Because again, x always lies. And so that would be our equation. There's nothing telling us that we're moving left or right or up or down. So we get 3 times the absolute value of x divided by -2. Again, 3 is our vertical dilation, and then -2 is our horizontal dilation. If we look at C, again, C here is going to be just a little tricky. If you look at this, y minus 2 divided by 3, you're dividing that whole thing by 3. So what you can really say is this is y divided by 3 minus 2/3. You can break up that fraction. And so when you look at this, you see, okay, my horizontal dilation is 2. I'm moving right 1 unit, okay? And so what we have, if we're going to write our equation, it'd be y equals, our absolute value of x would be, it'd be x minus 1 divided by 2. And then if we look at this as it's rewritten, we see that our we are subtracting 2/3, so that means we're moving down 2/3. And we are dividing y by 3. Again, this mapping notation does not lie, so we would divide by 3, but dividing by 3 is the same as multiplying by 1/3. And so we get this equation right here. So again, what you're doing is you are taking your transformations to your x and writing them inside the absolute value brackets. Then you're taking your y values, what's happening to your y values, the vertical dilation and the vertical shift, and you are adding or subtracting the translation there and multiplying by the dilation outside. So you try B and D and then check your answers on the guided notes. The final thing that we need to talk about is we need to take a look at how to go from a graph to an equation. So again, when you're looking at these graphs going to an equation, the first thing you should look at are dilation, or are translations. So first, translations, and then second, dilations and reflections. So by taking a look at this first graph here, we see that this is an absolute value graph because it is a V shape, and we see that the vertex of that is now at 3, 4. So again, the vertex of the parent function is usually at 0, 0, so it has moved 3 to the right and 4 up. So if we are going to write this with just that translation, we would have x minus 3 plus 4. But we can see that there have been a few other things that have occurred. So the first thing that we should do is find out our dilations. In order to find the dilations, or define the dilation for the equation based off of a graph, what you're going to do is go, in this case, to your vertex and find your next nice point. Typically, I will give that to you. And then what you will do is count the horizontal change and the vertical change from the vertex to the next nice point. So we have 1, 2, 3, 4. So that's a horizontal change of 4 and a vertical change of 1. And so what that tells you is because we have a horizontal change of 4, our horizontal dilation is 4. And our vertical dilation is just 1, which you don't technically have to put the 1 there, but we will. Now you have to take a look and see, were there any reflections? And you should notice that because this V-shaped graph is opening down now, there was a reflection over the x-axis. So we had to throw a negative sign in front of the 1 because that is where our reflection of over the x-axis occurs. If we take a look at this next graph, this is a quadratic equation, so we know it's going to be of the x squared nature. And so again, you want to take a look at where is your vertex. This vertex is at -4, -6. The parent function is at 0, 0. So that we know that this function has shifted 4 units to the left, so x plus 4 squared, and 6 units down, -6. We also need to figure out what were the dilations that occurred. So again, you take your vertex and then you take your next nice point. The horizontal change would be 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8. So there's a vertical dilation of 8 and a horizontal dilation of 2, and so this would be your equation for that graph. Taking a look at a rational equation, we can see that this graph has shifted right 4 units and down 3 units. We know that because the asymptotes that we have are intersecting right there at that purple point. Typically, they intersect at 0, 0. So we'd have y equals 1 over x minus 4. And then we'd have minus 3 because it's shifted down 3. Now, the next thing we need to figure out were there any dilations? So you want to find a nice point, which typically, again, I will give you. And then you would count from the intersection of your asymptotes the horizontal and vertical change to that next nice point. So 1, 2, 3, 1, 2. And so what you see is that there's a horizontal change of 3, or horizontal dilation of 3, so you have divide by 3. And then you have a vertical dilation of 2. And then the last thing you need to check is, were there any reflections? Typically, the rational function, the parent graph, would look like this. And so you can see that this blue piece over here has reflected over to here. And so what that tells you is that there is a reflection over the y-axis. And so what we have is, because there's a reflection over the y-axis, we'll put a negative sign right in front of the parentheses of x minus 4. That tells us that there's been a reflection over the y-axis. And so you have this equation. Now this equation could be rewritten algebraically as y equals, you'd have 2 times 3 over negative x minus 4 minus 3, which would then allow you to write it as 6 over negative x minus, or plus 4, negative x minus 4 minus 3. And so that equation is the same as this equation. Okay. Again, that was a quick rundown of those how to find the graph from how to find the equation from the graph. There are some extra examples down here. Don't worry about number 1, but maybe go ahead and try to look at 2, 3, 4, 1, and 2 and graph those on your own. And if you have any solve those on your own, you can check your answers on the completed notes. And if you have any questions, just let me know.